at the end of class, remind me, please, before class ends, I need to pass these out. But I want to do it at the end of class.
Oh, I didn't know.
So we're not like looking at it the whole time?
Yeah, okay. I did not know.
That's too well.
It's not just this class. Everybody does that.
Oh, okay. I was wondering what it was asking. I was just looking at it. I was like, what is the with that? No, because when I read the question, I even asked physics majors, like some of the juniors. I was like, what does this question mean? They was like, I don't know. Oh, it's like they was just like, oh, I don't even know what it's asking. I was like, exactly.
Yeah, first of all, I went to at least 2 computers yesterday, and none of them really knew any of the answers to your questions. It took at least 20 minutes to figure out the answer.
Where did you go?
To the physics help place.
Physics Learning Center?
Yes, physics learning
And
center.
they don't know how to do the
Well, no, it was the law of cosine, law of sine. And I went to tutoring in the library.
These guys are wondering if
You do it with dot and cross product. One dot and then okay.
Yeah, like okay, it's like built into dot and cross product.
Almost? Yeah. It's almost built in.
Okay, that's kind of how I like thought of it, but
We'll go over it in class. So you'll see.
like the one how to defining the law of cosines.
It's okay if you use the cube
Or using
instead of
vectors.
like a.
No, okay, I did, but I
used the cube.
The only reason I remember AAA is because of that movie. So my bad.
I think so. The major diagonal of the cube. Is that what you mean?
I've never heard
It's
of
the
it.
one where
I've never seen
Zach
that.
Logan asks
I
whatever his name
drew
goes
so many
across.
cubes and squares and
Whatever he has
parallelograms
cross
and triangles
with,
yesterday. I'm talking like
Whatever.
probably 30.
Iron
I
Man.
probably did 30 of them.
I'm not
Robert
really
Downey
sure.
Jr.
Robert.
Seriously?
Oh yeah, what's that movie called? That's not movie.
Seriously?
Yeah, the two of them go
They're
across
just
country. What's it called?
pages of
Q Day, isn't it?
Yeah,
The first problem, the Pythagorean theorem. The Pythagorean theorem in 3 dimensions. Is that
The
what?
first, you were 3. The 3 from the book were fine. You were 3 for like, I just had to draw.
Yeah, the Pythagorean theorem.
Yeah, I just.
Okay.
I already turned mine in.
Yeah, I bet.
Yeah, I would like to.
But I've never seen it.
It's alright.
Clearly.
Oh no. They make a whole movie based on these 2 astronauts.
Yeah, we got everybody here, so let's get. It's time to start anyway. Okay. Has anybody sailed? Any sailors in the bunch?
I've sailed before.
Can you sail faster than the wind?
No.
They sail faster than a wind.
Watch. So it works by they have these foils that come down under the hull and then they curve in like this, and they're wing shaped down on the bottom. And the thing that's going fast enough is like a wing in the water, and it lifts the boat up out of the water. It gets lift, and the boat's now the only friction acting on the boat is what's going over the wing down here under, and that's the only thing that's left in the water. The wings have to be really strong. They're carbon fiber composite material that can withstand many times its own weight. And so it's very high strength, low weight material. The whole boat is made out of that kind of stuff. The thing is 17 stories tall, the sail, that main sail. That main sail is a solid piece. It's not fabric. Well, it's not solid either. It's hollow, but it's got ribs and then it's like saran wrap on the outside. It's fantastic stuff. This is going on in San Francisco Bay, the America's Cup. It's this week, so you can watch it on.
Sailing thing?
It's a sailing, yeah, it's like the sailboat race, but it comes down to 2 boats. They sail head to head, 17 races, and the best of 7 boats are going. The races last. These boats are going so fast. They're over a lot shorter than they used to be, but the race will last. I think it's under an hour each one. They'll do 2 in a day. It's the Kiwis, the New Zealand team against the U.S. team. U.S. team is down a lot now. The New Zealand boat is a lot faster.
Yeah, we beat Mexico in soccer.
And it's not restricted to. Hold on, let me. That looks like it's a little hard to do. I'm sure it takes a little practice. a lot of practice. But the people who design those America's Cup boats, there are physicists on the team, and they work out the design of the boats, because the boats change every year. They're different design, and they're radically changing. Even though the two boats look a lot alike, there's still some differences between them, and they must have made about 6 of them and picked the one that was the fastest to use for the race. It's gotten to be big business. So Oracle is a big sponsor of because of computers. Who's the New Zealand team? It's another computer company. Anyway, I had to show you this. Okay, so let's turn to some more fundamental stuff besides physics of sailing, which is really cool, I think. And let's go through the homework. So this is the last homework for Chapter 2, Part A on vectors. So you will start now Part B. We'll do the reading for Part B for Friday. So let's go through the questions for the homework. These were intended to get away from just the mechanics of dot and cross products and try to get you thinking more about what they mean.
Are we allowed to look at ours, or?
No, I'd rather you not this time. Yeah. So that time when there was a lot of mechanical stuff, I was happy to have you learning about the mechanics. This one is one I'm really wanting you to think about the process of what dot and cross products mean. So let's look at that first one. The question has to do with the three-dimensional Pythagorean theorem. You know the two-dimensional theorem, which is that the it did it. See, yeah, it froze up. So we've been working on this, trying to figure out why it freezes up, and they thought they had it solved. Okay, the two-dimensional Pythagorean theorem. If you have, and let's think of it in terms of vectors, the length of a vector whose components are x and y in 2 dimensions, the length will be square root of x squared plus y squared, right? If you go x in one direction and y perpendicular to that, then the total distance you've traveled is the square root of the sum of the squares, like that. What about in 3 dimensions? Suppose you have a vector in 2 dimensions. Let's call it r, just because it's a displacement. Let's do it that way. A 2-dimensional vector, you are displaced by that much. The length is then just x squared plus y squared, which you can get by the dot product of r with itself. But we know that that's the length from the Pythagorean theorem. So now the question is, what about in 3 dimensions? This is 2. Does the same thing hold in 3 dimensions? If I have a vector in 3 dimensions, I go along 3 perpendicular directions and amount x, y, and z. Is the length of that vector, this is the question, equal to the sum of the squares of the components, like that? And this would correspond, in fact, to the square root of r dot r. So, but we haven't proven it just by showing that the dot product and using the vector algebra we've demonstrated that in 3 dimensions it in fact is the length, right? I asserted that, but we haven't proven it. So this first exercise is to demonstrate that. So the way to do that, and one easy way to do it, is to consider this in 3 dimensions. So I'm trying to draw this in 3 dimensions, a little difficult. So this is x direction, the y direction, and the z direction. Okay, and we have some vector in general r, which is pointing out some way out inside of that. Let's project that down into the plane and consider only the parts of it in the plane. So along this direction we have x, and we get that by drawing a perpendicular over to the x-axis. That's the x component. And we have a component along the y direction, and we get that by drawing a perpendicular over to the y-axis, so that's the y component. And you can see then that in the xy plane, the length of this vector, which is not the full vector, but it's just a part of it that's in the xy plane, the length of that piece is indeed equal to the square root of x squared plus y squared, using the Pythagorean theorem, right? You see that much? Now the third part that we're missing here is the part that's out of the plane, which is the z component. And now let's draw that triangle over here. A triangle formed by r, and then the perpendicular part, which is z, that is the part coming up out of it, and then this third piece here, which has length squared of x squared plus y squared. You see that triangle? Is everybody okay with that triangle, where that one came from? I'm taking this length and that vertical part, and that the vector itself forms the hypotenuse. So I form another triangle there, and that gets me the triangle that I want. So I need to use, again, the Pythagorean theorem to calculate the length of that, because I've got another right triangle. How do I know that this angle is a right angle? Because z is perpendicular to the xy plane. So it's a right angle. Okay, so now I want to compute the length of that thing, and the length of that thing is going to be the sum of the squares of the components. So here's one side, the square root of x squared plus y squared. I've got to square that, and then I add it to z squared, and then I take the square root of the whole thing. Okay, and then I get x squared plus y squared plus z squared. So that is, in fact, the generalization of the Pythagorean theorem in 3 dimensions. There's other ways to do it, I'm sure, but this to me seems the easiest. All right, so this is one of those problems you either see it or you don't, right? You know, it's kind of one of those things you got to puzzle through. Maybe you come upon it yourself. Maybe it's never really quite comes until somebody shows you something. But after that, it should be something that you can see. Right? You understand the point of it? This looks like the Pythagorean theorem, but it's not the Pythagorean theorem exactly. It's a 3-dimensional generalization of the Pythagorean theorem. And so what we've done is to prove, based on the 2-dimensional Pythagorean theorem, we've extended it to 3 dimensions. And you could keep on going if you had something that was 4-dimensional, which we can't draw. I have enough trouble drawing 3.
I feel like I should know this, but the only question is, why is the length of that line? Well, I guess the line square root of x squared plus y squared.
This one?
Yes, sir.
Okay. So that's the Pythagorean theorem in 2 dimensions. So let's see, if I had another color, I wonder if I could add a color here. Let me see. I think there is a way to add another color.
Can you click on that color palette up there at the top?
Do red, blue, red, and green.
Up here?
To your right.
Ah, there we go. There you go. Okay, here. Ah, green. Good. That was good. Thank you very much. That's y, right? That length is the same as y. Okay, so now we have a triangle here in the plane, x, y, and then that length, which is that piece right in the middle there. And that's perpendicular because we chose x and y directions to be perpendicular to each other. So this is square root of x squared plus y squared. That's what we assume that that's true, starting with the Pythagorean theorem in 2 dimensions. Does it help? Okay. All right. Now, the next 2 are a little trickier. They do take a little bit of work. And so we need to remember what is the law of cosines and what is the law of sines. And I give you a hint in both cases about how to do this. So the law of cosines and the law of sines all involve triangles which are not necessarily right triangles. So don't start off by drawing right triangles, because you may be dealing with a special case if you do that. So it's better to try to draw something that's not a right triangle and label the sides A, B, C, like that. That's the length of the 3 sides. And then the angles you name corresponding to the angle that's on the opposite to the side. So I'm going to call this one alpha, corresponding to A, beta corresponding to the angle that's opposite to B, and gamma is the angle opposite to the side C. Is everybody okay with that so far? Now I can write down both the law of cosines and the law of sines. So the law of cosines, let me do the law of sines first. We'll come back to it. I'll write it down. The law of sines, A over sine alpha is equal to B over sine beta is also equal to C over sine gamma. Is that not familiar to you? Have you not seen it? You might have had to look it up, but that's the law of sines for a triangle. It's true for any triangle. It's a rather remarkable thing. You divide the length by the sine of the angle opposite to it, and it's the same for all three. Interesting. Right. So the three sides are obviously related in their length, and the three angles are obviously related. They add up to 2 pi, right? To pi. They add up to pi. But they nonetheless have this relationship. There's another one called the law of cosines, which could be expressed in 3 different ways. So I'm going to write it down first this way. The length squared of one of the sides is related to the other 2 sides and that third angle, A and B, and then the cosine of the angle that's opposite. So that side, the length of that side, can be calculated if I know the length of the other 2 sides and this one angle, which is opposite to C. And that's that right there. Special case of this, what if gamma were pi over 2? Suppose we had a right triangle.
It would be the Pythagorean theorem.
Exactly, right. So if gamma is pi over 2, so if that were a right angle, cosine of pi over 2 is 0, and we would have here the Pythagorean theorem. So the Pythagorean theorem could be considered a special case of the law of cosines. So this works for all triangles, not just right triangles. So you could also write this in terms of any other combination. So A is b squared plus c squared minus 2bc cosine alpha. B squared is ac squared plus a squared minus 2ca cosine beta. So there are actually 3 of them. But I think you might be able to prove, if you could add 1, you could prove the other 2 from it. But in any case, I only wanted you to try to do it for 1. Certainly, if you could do it for 1, there's nothing special here about any of these angles or any of these sides. It's not a right triangle or anything, so it should hold for permuting these things. Okay, so that's what you were to try to look at. You're going to use vectors to see if you could investigate those things. Okay, so let's do the law of cosines first, and the way we can do this in terms of vectors, let's turn these into vectors, these sides, A and B. So it's a vector of length A in the direction of that side, and then there's a vector B, which is of length B in that same direction, and here's C. Now we have the vector identity. C is the sum of A and B. Right so far? Just do it as a vector relation. The 3 sides of a triangle, if I make vectors out of them, will obey the vector relation. All right, now, how do I find the length of C? If I know the vector, how do I find its length?
Do you know the angle?
Which angle?
Between A and B.
Yeah, but let me just ask a more general question. If I know C, just any vector, even just by itself, if I know the vector, how do I find its length? Take the dot product with itself, right? The dot product of any vector with itself gives a number, which is the square of the length of that vector. So the square of the length of the vector is just c dot c, correct? True for any vector. Well, this one is the sum of 2 vectors. Oops, that's a plus here. Let's see about that works. It works. Okay. Okay. Now anybody see the next step?
Foil.
Sorry?
Foil.
Foil?
Or, yeah, A times A plus A.
Yeah, so we're distributing the multiplication over the addition, right? Is that what you call foil?
Yeah.
Or are you going back to the sailboat with the foils?
No, it's just a word.
The way a lot of
First
the way a lot of
outside,
distributed
inside
property was foil, first outer inner last.
Ah, that's what that means. Okay. Yeah, first, outer, inner, last. Right. FOIL. Gotcha. Okay. So we have how many terms? 4. Now with dot products, it's not important to keep the order, but I do manage to keep the order here. With cross products, absolutely essential to keep the proper order. If we were doing this with cross products, then you'd have to be careful to maintain the order. In other words, we get here an A dot B, and we also have a B dot A. For dot products, those are the same. Cross products, they would be opposites to each other. A cross B and B cross A are opposites to each other. For dot product, it's the same. Okay, so what is A dot A? Square of the length of A. And what is B dot B? The square of the length of B. But now we have this 2 times A dot B, right? It's the same. Whether we write it as A dot B or B dot A, that's the same, correct? Now, let's notice this. What is A dot B in terms of the definition of the cross product? No. Why? They're not perpendicular. These two vectors are not perpendicular, right? Say it again. What's the fundamental definition of the dot product in terms of magnitude and direction of the vectors? Somebody may be saying it. No? Anybody else? No? AB cosine theta. That's the fundamental definition of the dot product, right? If you said it and I didn't hear it.
Oh, no, I was just talking to myself just now.
Gotcha. Okay. All right. Times the cosine of the angle between them. But be careful here. What's this angle?
C.
No. Well, C is the length of the side. But look here. The angle between them is this angle here. Let's do this in red. This angle here. Right? I'm going to extend A out a little bit more. That's the angle. That's theta.
Why is it that?
Yeah, because it's the angle between the two directions. A and B.
Because it's pointing that.
Yeah. So that's the angle. But it is related. That angle, how is that angle related to, let's do green here. How is that angle related to this angle? And what is that angle in green? We gave it a name earlier. Gamma. That's gamma. Okay, so the cosine of gamma, the cosine of theta is AB times the cosine of pi minus gamma. And what's the cosine of pi minus gamma? That's the negative of cosine of gamma. So you can remember that if you remember the addition of two angles, the cosine of the sum of two angles. That's one way to remember it. That's maybe the easiest way. Cosine of two angles, A plus B equals cosine of A cosine of B minus the sine of A sine of B, or the opposite of that is cosine of A minus B. It's the cosine of A cosine of B plus. That's involving the difference. Okay, and if B is gamma, if A is pi, then you will get, yeah, that's right, minus, yeah, you'll get the cosine of pi, which is -1, and that gives you a -1. Okay, so coming back to what we had then here, c squared is a squared plus b squared minus 2 times a dot b, which is ab cos gamma, and that is the law of cosines. And that was the crucial part there, was remembering this piece here. That's the fundamental definition of the dot product. That plus setting up the sum of the two vectors to get the third vector, and then taking the square to get that. Would you like me to go over that again?
Would you mind scrolling down again?
Pardon?
Would you scroll down again?
Sure. And remember, all of this is, has anybody been watching any of the recordings?
Yeah, here and there.
Here and there. Okay. And also the podium notes. Anybody make use of the podium notes? Is that okay? And if you have them together, if you're watching the lecture, you've got the podium notes. It's maybe helpful. Okay. But I'm not discouraging. I don't want to discourage questions in class. That's not what I mean. That's not my intent. I just mean that it may occur to you later. What was that now? And you can go back and watch it again. Okay on that? All right, let's do the law. Go back to do the law of sines. Same trick. Let's reconstruct this triangle in terms of vectors. So let's go back here. We have A and B. And we could construct C here, but I don't really need to do that. So I'm going to erase that one. Don't really need C. I'm going to put C inside here. Don't really need it, but it's the sum of those two. How would I go about calculating the area of that triangle if I know two of the vectors?
Take the cross product and then divide it.
Yeah, divided by 2. It's exactly half. Exactly. So let's write this parallelogram here. Let's draw that. Remember, the cross product, the magnitude of the cross product is the area of that parallelogram, and that triangle cuts it in, is half of the parallelogram. So the area of that triangle is going to be, the area of the triangle is going to be 1/2 of the magnitude of that vector, which is A cross B.
I thought that was too easy.
Can you see it coming? What's the fundamental definition of the cross product? Remember, the fundamental definition of the dot product is AB cosine theta. Fundamental definition of the cross product is AB sine theta times what? There's a vector. What's the vector? What's the direction of the cross product? N, which is in this figure, where does N point? For if I do the cross product of A and B, and it's coming up, right? So, and the magnitude of that vector, the magnitude A cross B, so A cross B is going to be the normal to the plane of the figure times AB sine theta. And remember that angle theta, oops, that's theta there, be careful. We've got to go back and do that. Magnitude of A cross B is just AB sine theta. Now let's watch it here. That angle there is the same theta. Remember? Can you see why it's the theta? It's the angle between A and B. A is this way, B is that way. This angle in here is that theta. You've got to be careful of don't just throw angles around thinking that any old angle will do. It isn't going to work like that. This is the angle theta here. Now, how does that relate to this angle? Gamma. Yeah, it's the same as they're supplements. And so this is AB sine of pi minus gamma. And that is the same thing as gamma, AB sine gamma. The sine of pi gamma is the same, sine of pi minus gamma is the same as sine of gamma. These are trig relations. And again, you can get that by looking at sine of A minus B, sine of A cosine of B, minus cosine of A sine of B, and then putting in that A is pi, so you get the same thing there. Okay, so the magnitude of that is AB sine gamma. All right, so the area of that triangle is AB sine gamma. So what we did, we took two sides, and the angle here is the angle opposite to that, of course. We could use two other sides. What if we used A and C? Then we'd have the length of A, the length of C, and we'd have this angle, right? Which is beta. And if we took B and C, we'd have that angle, which is alpha. So but does that change the area that's calculated? It's the same area. It's the same triangle each time. So this is AB sine gamma, BC sine alpha, CA sine beta. All the same. Okay. See the next step? It's going to be upside down from the way I wrote it. But that's all right. What's the next step?
You could get rid of the extra.
Get rid.
You can divide each one by B, and then divide each one by A, then divide each one by C. And
Divide them all by ABC.
Then eventually you'll get blah, 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 and this over the corresponding length.
Divide by ABC.
Yeah.
So this is sine gamma over AB. Sine gamma over ABC is sine gamma over C, right? It cancels AB. Sine alpha over A, and sine beta over B. This is not the way I wrote it. I wrote it in terms of A over sine alpha, B over sine beta. So it's the inverse. And that is the law of sines, which you can prove using the cross product. No components. We just use the fundamental definitions of cosine and sine. So this is an exercise in trying to get your mind around what these things mean. Okay. The other one, there's another one that I want to do, which is actually the last two on your homework are very important. Is it the last two or the last one that has two parts? I think it's it has to do with the uniqueness of the dot product and the cross product. No, with the inverses of dot product and cross product. We've developed multiplication. So we started with vector addition, and we're trying to make a vector, an algebra of these vectors. It's analogous to the algebra of numbers that we know. So we developed addition and subtraction. So we clearly had an addition and then an inverse, just like we have a vector and its opposite. So the opposite was the additive inverse. So if I have a vector A, negative A is the opposite direction, and I add the two vectors and I get 0. If I go that way and then back the same distance but in the opposite direction, I come back to where I started. That's an inverse. So addition has an inverse. Then we went on to develop multiplication, multiplying vectors. Like we multiply numbers, we want to have multiplication. And we thought of two different ways that we could generalize to find something like multiplication of vectors. There may be more ways, but these are the two common ways. Now the question is there a vector division? Can you divide by a vector? So the answer is what? What do you think?
You
No.
can multiply.
Why?
So that's what that
Because you
question
won't be able to tell what direction you're supposed to go.
Exactly. There's no way to determine the direction, and that's the problem. Now there is a way to do it. There is a way to kind of do it, which involves what's called tensors. We're not going to get into tensors now. There is a way to do it, but in the simple way of thinking of it, no, you can't do it. Let's figure out an example. Let's suppose we have some vector. Really, again? I tell you. Okay, that's twice today. Every time I step away, if I don't write on it, it seems that there's nothing in here which is supposed to be going to sleep, though. There's no sleep mode on this thing, so there's something not quite right. Okay, let's let me draw a figure here. Let's suppose we have a vector A here. Okay, I'm going to draw a vector B, a vector C, and a vector D. And all those three vectors, if I drew them correctly, they would all have something in common. What's that?
The same dot product today.
Yes, sir. Mr. Flanagan's caught on here. They all have the same dot product. So let's draw a red line here, vertical red line. I've got to fix my drawing down here because this one doesn't quite have the same. Another one here. Okay, so let's call this one B, C, D, and E. 4 different vectors. Let's do another one straight along. It's in the same direction as A, F. 5 vectors. They all have the same dot product. A dot B is the same as A dot C, is the same as A dot D, is the same as A dot... You get the idea? Why are they all 5 the same? somebody other than Mr. Flanagan. He's got clearly in mind here.
Because they all got
Mr.
the
Avery.
same horizontal or parallel component compared to A.
Right. Remember, A dot any vector is going to be the amount of V that's parallel to A. And all of these have the same component parallel to A. All of those vectors. Which is another way of saying it. Remember, you're projecting this vector onto the direction of A. That gives you the parallel component. So that means that the inverse is not unique. If I know the dot product, I know, say I have some other vector G. A dot G is the same as all of these, is equal to some number. And I know A, but can I find B? Can I find G? Not uniquely. Because I don't know the amount of the vector perpendicular to A. I only know the amount of the vector parallel to A. So therefore, I don't know the whole vector. So I can't divide. I cannot divide by, say, divide by A to find G. Doesn't work. You're losing information. It's a projection. That's another way of thinking of it. You're projecting out the part of the vector that's parallel to A. When you project, you lost what you didn't project. You threw away something, so therefore you can't reconstruct it.
If one of those vectors that cross the red line, it would not have the same dot product.
Correct.
Okay.
If the head of the vector, so they all have the same tail, if the head of the vector does not lie on that red line, then it doesn't have the same dot product. But there are a lot of vectors that do have the same dot product, so it's not unique. So here's the important lesson. Cannot divide. Cannot divide by a vector. No unique answer to that operation. Can't do it. Even though you want to, you really want to in various problems, you want to just divide. It would be so easy if I could just divide. Can't do it. Yes, sir.
What about for cross products?
All right, that's next. So what about cross products? What do you think about cross products? Mr. Flanagan's way ahead, so I'm going to hold him back a little bit.
You'll get the magnitude and the direction of it, but you'll just know that it's based on y and x, but you can have many different variations of y and x to get that same magnitude.
Yeah, so are there, just like with the dot product, is there more than one vector that gives me the same cross product? If I have vector A, and I'm going to cross that into some other vector, are there lots of other vectors that give me the same cross product? So let's do that again. Let's talk, here's A. And now I'm going to take the cross product with some other vector. What part of the other vector comes into the cross product? The perpendicular component. So any two vectors that have the same perpendicular component, as long as they're in the same plane. Right? So let's consider this plane. Let's do it two-dimensional. And I want to construct a lot of vectors. I have a lot of vectors. If I draw a line across here, any vector that begins here and ends here will have the same perpendicular component. The perpendicular component is this piece. This is the perpendicular component, right? That which is perpendicular to A. So all of these vectors have the same perpendicular component. They all have the same amount perpendicular to A. B, C, D, E, F. Again, A cross B is the same as A cross C, dot, dot, dot. As long as the vector ends up tail to head on the same line there, same cross product. Has the same area of the parallelogram. If I construct the parallelogram out of these two, and I just slide the parallelogram over, it's a rectangle here. All right, so they all have the same area because it's the length times the height for a parallelogram. They all have the same area. It's another way of looking at it. So, cannot, again, moral of the story, so I know A cross B is equal to some vector not C, but some other vector, let's call it G, cannot divide by A. To find B. Doesn't work, because you don't know what direction you're missing the piece that's parallel to A. When you take the cross product, you project out only the part that's perpendicular, and you lose the part that's parallel. So it may be, if you knew both the dot product and the cross product, that you could find the vector. Okay, now maybe we're narrowing it down, because that's got to be on two different lines that cross, so maybe there's one unique answer there. I'm going to postpone that one, the discussion of that one, but it's certainly something a lot closer. Okay? But this one, again, is to illustrate the nature of the cross product and the dot product. I want all these exercises are to try to get you to think of these vectors away from thinking of them as components and thinking about what the fundamental definitions are. Does that help? Okay. Any questions about the first part of Chapter 2? I'm not done. We're gonna start Chapter 2b now. We're gonna start calculus now. Most of the time I'm behind the book. Occasionally I'll catch up and I'll talk ahead of the book. So the second part of Chapter 2 is calculus. Okay. So you often hear, I'm not going to write it because I don't want to reinforce it in your mind, but even saying it, but just because I want to tie it into stuff that you know and sometimes set it up and try to knock it down. Have you heard what is calculus? There's an expression, a common.
Math of motion.
Sorry?
Math of motion.
Math of motion, mathematics of change, right? That's what they try to explain. Yeah, right. We're going to knock that down. It's not quite right. It's not a good way of thinking of calculus. What is mathematics about? Quantity. Math is the study of quantity. Quantity as quantity does not change. Square. Square forever. The concept is an immutable thing. It does not change. 2 is 2 forever 2. It doesn't change. Quantity and change are different from each other. So what is change? And so I want to talk just a few minutes about what is change. Dr. Rizzi in the book does not make this mistake. He's very careful to lay out for you what calculus is. So I want to go off track just a little bit while you're reading to get you thinking about this. What exactly is calculus about? It's related to quantity in some way. So let's briefly talk about change. What is change? Yes, sir, Mr. Flanagan.
The actualization of something's potential.
Ooh, where did you get that? Is that in the book?
I don't know. I was just using the active potency terms that were in the book for chapter 1.
Oh, man. All right. Good job. I'm not going to write. Yeah, all right. I'll write it down because it's so good. The actualization. Where did you get that?
You make it look better.
The actualization. Actualization of potency, better the act of that. This is Aristotle, classic Aristotle. The act of that which is in potency as such, but that's kind of a formal definition. So let's talk about, there are two words that are key to this, act and potency. So everything that is changeable is a combination of act and potency. It actually is one way and is potentially some other way. And everything around us is a combination of that. And the fact that it is changeable tells you this. Even if it's not changing at the moment, it has that possibility to change. There's nothing around us. Nothing that's subject to physics. In fact, physics is the word coined by Aristotle, referring to the changeability of things. Physics is the study of changeable things. That's where the word comes from. Aristotle coined it to refer to the study of changeable stuff. So it is one way, but it has the potency to be another, can be another. Remember, what was the definition of a physical thing? Actually is something, can be some other way. Can be something else, can be some other way. Physical things are a combination of act and potency. So, act is obviously real. It's obviously real. You're actually, actually wherever you are. I'm actually here. I'm potentially over there. Now the potency is real, but it's a different kind of being. It's not as high as actuality. So I have the potency to be over there. A baby has the potency to be mature. Right? So those are examples of potency. There's lots of examples you can give. Any change can be that exists, any change that happens, you can identify there's an act and a potency associated with that. So I'm here, actually, potentially over there. Okay, now what was potential has become actual. That's the actualization of the potency, right? It was potentially, I was potentially over here. Now I actually am over here. Oh, but I potentially could go back, so it could be reversed. I could do this again. So change is a process. In order for change to occur, I have to have two states of actuality involved at different times. I'm actually present here. Later, I'm present here. Two different actualities. So, maybe that helps you to see why change is not on the list of properties. Nobody remarked at the time that change was not on the list. There's no 10th category with change, or there wasn't change anywhere. Change is not a quality, change is not a quantity, change is not a relation. Because what it represents is one property at one time becoming a different property at a different time. So change involves time, and in fact, time is the measure of change. Change is not then a property itself. Change is a process. Very important thing, very fundamental. Seems really simple. Very common mistake to think of change as being a property of something. If I take a pot of water, I put it on the stove, turn on the burner, and I put my finger in before it gets, before it heats up, and it's kind of tepid because it came out of the tap. And I wait a while, and it's definitely warmer. Wait a while, and this is going to get painful if I keep doing this, right? So what's going on? At any time it has some temperature, which we describe in terms of how hot it is. But change itself is not a property of the water at any time. Change is revealed to us because it has, at different times, different temperatures. That's change. It's a process of going from one temperature to another. So it's a coming to be. And in that sense, coming to be, or a becoming, it's the being that's coming. It's on the way, goes from one act to another act. So it's a process, and that is change. So we're going to talk next in next class. You're going to read about this. So in some way, though, we can relate two properties at different times. Suppose we measure the distance from that wall to here, and then I move, and then we measure the distance from the wall to here. Now I have two different measurements taken at different times, and I can compare them to each other because they're numbers, right? And I can compare two lengths to each other. But they have to be at different times. But nonetheless, I can, as long as I can remember, it was that far, now it's that far, I can even do a vector difference between them. It went from here to there. The vector represents a change in position. Right? Now I've quantified it. I've reduced something down to quantity. I could do the same thing with qualities. Shape, hardness, softer, it gets hotter. I can, as long as I can measure the quality. Remember, it doesn't essentially reduce the quality to quantity, but I can measure it, and then I can take the difference of two measurements Okay. But what is left is quantity. Measurement always reduces it to number. And I can look at how the number changes, but the change of the number is not fundamentally the same thing as the change of the thing itself. Change of place and change of number are two different things. In one case, I'm representing it, change of place by change of number. So I've quantified it, but it does not capture the essence of what happened. It's just a change of numbers. Okay, but it's that process of quantification that's going to lead us to the calculus. It's very important. Really potent stuff. Okay, let's see. On your way out, please, I'm going to hand out, I've got lots of backlog here, homework, tests. I'm going to hand them out. And so please pick up the solution. I wanted to give you feedback on the grades for the test, this grade distribution. So generally speaking, I think this was a pretty easy test. Generally pleased with the